So I want to finish up one more problem in mutual inductance before we move on. And it's this problem here. Now, most of the time when we use mutual inductance, we use a mesh analysis, we use loop analysis. And if you look at this one, we'd end up with 3 loops. This first loop would be fairly easy. Then we'd have another loop, and we'd have another loop. But we have 3 loops. So what I thought we might do is look at taking this first part of this circuit here and using a source transformation on it. Start to use our tools that we've learned in the past. If you have a current source that is in parallel with a resistance, can we replace that essentially with a voltage source that's in series with resistance? Absolutely we can. That's a source transformation, or the difference between a Norton and a Thevenin model, however you want to think about it. So what I do is I can figure out the voltage source. By Ohm's law, V is equal to I times R. So if I take that 5 at 0 and multiply it by the 60, I come up with 300 volts, so that's the voltage source, and I just move that resistance right up there. So you could definitely do this problem. That wouldn't be a problem. It might be a good thing to go home and try this weekend, see if you can get the same answers. But I'm going to try and make my life a little bit easier and tackle this problem. Okay. Well, let's say what I want is the power dissipated in the 20 ohm resistor. So the power dissipated in the 20 ohm resistor. So I'm really going to want to find the 2 currents here. Let me talk about these currents then down here. I'll just go ahead and assume this current here, I'll take it as I1. I'm going to assume this current here, I'm going to take it as I2. This looks like an ideal transformer given the turns ratio. So I'm going to then assume this voltage across here, I'll just assume it as V1. And I'm going to purposely probably make this a little bit more awkward. Maybe I will take this as V2 across here. Okay? And I can assume those voltages and currents any direction I want. I tend to assume all my currents clockwise, and then I'll just put my voltages in there. And this voltage V1 is going to include not only the self-inductance term, but also the voltage that's induced by the current through this V2 because of the coil. Questions with that so far? So if I start to write my equations then, when we come up here and start to write the equations, I should have, if I work my way around here, as I go around there, I'm going to have a gain. So let me take that as minus 300 at 0. Should just be minus 300, but I'll take it minus 300 at 0. And then I'm going to go through this one, and I'm going to have a drop of plus, what, I1 times 60. And then as I turn and I go back through this one, I said this voltage here is going to include not only the self-inductance, but the mutual inductance part. So really all I have to do is think about going from positive to negative. Positive to negative would be a drop. So I'm going to say that that is plus V1. And that gets me then down to here. So I need to look at the current going down through that, which is going to be I1 minus I2. So I'll have positive 20 times I1 minus I2. Does that get me back to my starting point? Yeah, it actually does. And I don't have to worry about the mutual term because I'm going to deal with that in terms of V1 with those ideal transformer relationships. So I can say that's equal to 0. Now what I do have to concern myself with is how many unknowns do we have, how many equations do we have. It looks like I've got, what, 3 unknowns in one equation? So I'm going to have to produce at least 2 more equations that I know of. Well, let's do an equation for going around this loop here. Maybe I'll start right here and work my way through this, which would be then, we're going to call this equation 1. So why don't I write equation 2 here as 20 times the current going up through this is what? I2 minus I1. And then as I go from positive to negative here, That's going to be a drop, so that'll be positive. I'm taking drops as positive, positive V2. Okay with those? Double check some of these. Yeah, I think I'm okay. So positive V2, and then as I turn and come around through this one, I'm going to have a positive 40 times I2. And that gets me back to my starting point, so I can say that's equal to 0. So as I keep track of my equations and my unknowns, I did indeed add another equation, but I also added another unknown, that V2. So now I have 2 equations and 4 unknowns. So where do I go from here? Well, hopefully I can relate this I1, which I1 is going to be this current here, isn't it? There's I1. And this I2, there's that current I2. I can relate those 2 currents, and I can relate these voltages, V1, and I can relate these voltages, V2. And I'm going to use that handout that I gave you last time. It's also in your textbook. So at this point, we need to then generate 2 more equations. We have 4 unknowns. We need to have 4 equations. And we'll turn to our table here that we've used before. I realize this table is probably pretty small in the videos, maybe even in the PDF. I'll put the link to my website in the description of the video, and you can actually go and print it off in its original form from the video. Also, if you're going to need this on a final or something like that, I'll make sure I provide it to you in that setting. Well, so let's look at this. I've got an excerpt of the circuit here that we've been working on, and we need somewhere relating V1 to V2 with this table, and then also I1 and I2 with this table. So let's see if we can do that. Let's work first at the voltage. Remember, the top part of this table, the top 4 cases here, are for voltage. Which ones do we need here? In terms of the dots are alternated, so this one's not going to do us any good. That one's not going to do us any good. It looks like this one has the dots alternated, so I kind of like that one. V1 is positive, negative here. V2, it looks like our V2 is kind of upside down or opposite in relationship to this. So maybe if I put a negative here and a positive here, I could just put a negative in front of that, and we would then have a minus V2. We would have a negative out in front of that. Well, remember that we already have a negative right there, and we have a negative right there. So effectively, we've really just canceled that. So if I go along and use this, I could say that minus V1 over V2 is equal to minus N1 over N2, where this is, of course, our N1, and this is, of course, our N2. Well, if I rearrange that equation and tidy it up, I need to get to say N2 properly. There we go, N2. So if I tidy this up, what was N1? That was 4. And N2, that's 1. So I could really say that this gives me an equation where I have V2 is equal to 1/4 times V1. Does that make sense? I multiply both sides by V2, divide both sides by 4, and then I have a negative on both sides. Yeah, so I think that will actually be my 3rd equation as I move back to the other page. And then we need to deal with current. So I'll say that this is the one that I used. Well, if I look at the current, what do we have? Again, our dots are alternated, so I don't want this one, I don't want this one, I don't want that one. This one looks to be pretty good. And whether the dots were in the upper position here and the lower position there, or whether they were in the upper position here and the lower position there, the important part is that they are alternated. How about our current? I1, that looks good. I2, oh, I've got I2 going to the right, so it looks like I need to do the same thing here. I could say that I have, rather we cross that out and put that current going that way, and we would have a negative I2. And then I need to come over here and follow through with that, so I would have a negative there. So I could, if I were to take care of this, have a minus I1 over I2
is equal to n2 over n1. So if I rearrange this, what was n2? That was a 1, n1, that is 4. So rearranging this for I2, I2 turns out to be equal to 4. And I only have this one negative. It comes from having to flip that around, so I would have a minus 4 over 1, if you want, minus 4 over 1 times I1. Is that correct then? I2, 4, yes, that would be correct. And we would list this then as equation 4. So let me double check these here. V2. Yes, I think that's what we want, and I'll say that we were using that one there. So again, when we look at an ideal transformer, usually indicated oftentimes with this iron core here, we'll come and we'll look at our tables, particularly when they've given us the turn ratios 4 to 1, and we can come up with these additional equations. So we take the first two equations on the previous page, we'll go back there in a moment, add these two equations to it. We now have 4 equations, 4 unknowns, and we can solve the problem. So let's go back to that problem. Okay, so I have 4 equations and 4 unknowns. They live for that in algebra. We could go through that. You could, if you didn't have much of a calculator, you could take these 2 equations here and substitute them into those equations. If you got a little more powerful computational tool, you probably just put it into a matrix and solve it. Either way, let me go through the answers here. V1 is going to be equal to 260, and that would be at 0 volts RMS. We started out with RMS values. We'll finish with RMS values. V2 then is equal to 65 at 0 VRMS. I1 is equal to 0.25 amps RMS, and that of course would be at 0, and I2 would be equal to minus 1.0 at 0 amps RMS. So those are the answers for that. If you go ahead and solve it, 4 equations and 4 unknowns, and that's that. Remember that we're looking for the power, so I could say that the current in here, I through the 20 ohm resistor, is really equal to, well, we could say I1 minus I2, right? And you might say, well, couldn't it be I2 minus I1? Well, it's not going to matter because we're going to square it, right, for the power equation. So I could say that this is a quarter minus 1, which gives me 1.25, is that right? Yeah, 1.25. So power being equal to I RMS squared times R would be 1.25 squared times a resistor of 20, which nets me 31.25 watts. If it wasn't RMS, you'd have to put a half in there, but it's RMS, so I don't have to worry about that. Questions with that? Pretty straightforward problem. We did one very similar to it last time. We come up with the 2 loop equations, and then we use that handout sheet, those ideal relationships, to come up with those 2 other equations. Questions with that? Everyone's good? Okay. When I post the PDF for this, it'll have a page 2, which was this ideal relationships that we used. Your textbook on about page 390, I think, has something similar to this, but I just went back to a different author. I think you've got a copy of that. Let's finish up our discussion on mutual inductance with safety. Okay, so we have a situation here where we've got your house, or a house, 2-story house there apparently, and it's got the transformer. So there's our transformer here.
Okay, and we're running about, probably somewhere around 7,200 volts down to about 240 volts, so it is a significant step-down transformer. Okay. And you got this one wire coming in here between that one wire and ground. Usually they have a lower wire on this thing that's stretched pretty tight, so hopefully when people start hitting that, they don't go any further. And this is actually hooked to ground here. So this is ground. This is then the hot. And between those two, you'll drop down to your 240 going into your house. So there's a storm comes along and it interrupts this wire here. All right? You don't have power in your house anymore, do you? Okay, so you're enterprising. You get your generator. You set that out here. You plug that into your house. Okay, and everything's good. The lights are now bright again. You got the party going. Either that or you got eyelashes on the windows, one of the two. But the problem is with this thing is this transformer, I mean, we normally have it running as a step down, but as we have this scenario set up, what's it running as? It's running as a step up, isn't it? So when the people in charge of the lines come to work on this, is there some potential here? Yeah, there is. Okay. Yeah, there is. So how do you avoid this problem? One thing that you can do is if you're going to backfeed your house with a generator is to turn off your main breaker. Okay, and that's probably a smart thing to do, because also what's happening with this transformer is your neighbor, you got your dirtbag neighbor here. Okay, and you have these wires also going into your neighbor's house, right? That's the way the power company's hooked it up. You drive through a neighborhood with above ground power, you'll see something just like that. So if you forgot to turn off your main breaker here, are you powering your neighbor's house too? Yeah, not that you don't mind, not that you wouldn't mind doing that. Maybe, I don't know, depending on how much you like your neighbor. But your generator may not be up to that task, right? Okay. So there's a few ways that you can avoid this. You could just run the generator in with an extension cord to certain circuits. Use it to cool down the refrigerator and the freezer and things like that. If you start hooking it into your house to be legal, you actually need to have some sort of a transfer switch. From a practical standpoint, you could still do this. I don't think it would quite be legal and it wouldn't be per electrical code. But if you turn off the main breaker, it won't backfeed back out of the house. So you have to be really careful of this. Transformers will step up and step down. And when we think of a transformer out there at the street normally stepping down, if you try and backfeed this with power from the generator, it's going to step it back up and could kill someone when they're trying to fix your lines, which they get pretty upset about for proper reasons. Okay. This was also true in the laboratory that you did this week, right? I said when you had that transformer and you didn't know whether it was going to step up or step down, you want to start testing it with a very small voltage, right? Because if it happened to be 1,000 to 1 step up and you put in 1 volt, what would you have out at the output? 1,000 volts. Okay, so you want to start very, very low when you're experimenting with that. And this is something that comes up quite often with transformer safety. Questions with that? Okay. Well, I wanted to, in the time that was remaining, go to chapter 14. We're going to start chapter 14. Which we're going to start talking about things that we've never talked about before, and that is what happens when the frequency changes. We hook up this circuit and we put a certain frequency to it, and then we vary the frequency. Some of you played around with this a little bit with the transformer, and the transformer did odd things as you changed the frequency, and that was good that you got to kind of look at that in a qualitative manner. We're going to try and look at this in more of a quantitative manner as we go along. Let's start out by thinking about an arrangement that is either in series or an arrangement that's in parallel. And we'll work, sometimes we'll work these simultaneously, sometimes we'll have to direct our conversations to just one or the other specifically. But if I look into the terminals on this and talk about the impedance here, I could say that that impedance Z was really equal to R plus j omega L plus 1 over j omega C. Pretty straightforward, right? And in this parallel case, if I looked in here, and instead of using the impedance, I'm going to talk about the admittance, which is 1 over the impedance, the inverse of the impedance. So I could talk about the admittance here being equal to 1 over R plus j omega C plus 1 over j omega L. And we want to ask the question, when does this look like a resistor? That might be one way of asking it. Another one might be has no phase shift. Those happen at the same point, right? If it looks like a resistor, it's not going to have any phase shift. We might talk about, we could use a fancy new term, resonance.
For the impedance, wouldn't it be negative 1 over j
No,
omega C?
because j is in the denominator. If I put j in the numerator, then it would be minus 1 over j omega C. So we could talk about asking, when does this look like a resistor? We could talk about, similarly, it would be the same point, it would be the same question, when does it have no phase shift of 0? We could talk about, when is it at resonance? I mean, if you're one of those people that want to go into power, you could even phrase this differently. You could say a power factor equal to what? Unity, couldn't you? Yeah. Okay, that's probably not a very common way of saying that, but if you want to mix it up yet further, we could talk about that. But we're probably going to, in chapter 14, mainly talk about resonance. The question comes up, when do we have resonance? But this being the same as these others allows us to answer the question, well, when does it look like a resistor? Or when does it have 0 phase shift? Well, that's when the imaginary terms cancel out. That is to say that j omega L is equal to 1 over j omega C. I could probably get rid of the j's in there. I think I'll say that omega L is equal to that. So that would be from here. Does this have the same conclusion? Yeah. We would say that omega C would be equal to 1 over omega L. Are those the same equation? Absolutely. Could rearrange those to get to that. So if I take, let's say, this equation, and I rearrange it, I could say that we have what? Omega squared times C times L is equal to 1. And then I get that omega squared is equal to 1 over CL. And finally, I say that omega is equal to, what, 1 divided by the square root of LC? Because, of course, the square root of 1 is equal to 1. Okay. And this is actually equal to omega naught, which is our resonant frequency. Okay? That's our resonant frequency. So if you want to come up with your resonant frequency, it's 1 divided by LC. 1 divided by the square root of LC. And that works on a parallel circuit as well as it works on a series circuit. Well, at resonant frequency, what does the impedance look like? We'll say this is Z sub R for at resonance. It really just looks like the resistance R. Or what does the admittance look like? The admittance at resonance is equal to 1 over R, isn't it? Okay, so it looks like a resistor. It has no phase shift at resonant frequency. So let's talk a little about this in terms of filter design or filter technology. Questions with this? Okay. So what do we mean when we talk about resonance frequency? Let's take a filter here. So we'll take a, first of all, maybe it's better to talk about where this comes from. We'll look at a circuit. And we'll talk about having some input.
and we'll talk about then some output, or we could talk about V in and V out across those terminals. And if I look at plotting the ratio of the output over the input, so I could say that I have V out over V in, the magnitude of that. Sometimes we'll say that this is H, the transfer function. So I look at the magnitude of the transfer function. Depending on the circuit values and whatnot, I could end up with something that looks like that, where it comes up to this maximum value, which is probably going to be pretty close to 1, and it happens at the resonant frequency that's going to be omega naught. So this is a classic bandpass filter. Okay. If you want to tune in a radio, because no one listens to radio anymore, but if you want to tune in a radio at a particular frequency, you want that frequency to pass through your circuit, and you want all other frequencies to be attenuated or to stop. Be a great application for a bandpass filter, right? Now there's some other filters that are out there. We could have a filter that looks like this, again, where we have the transfer function versus the frequency. And maybe we'll do something like this, which we would say would be a notch, or a band reject. What could that be good for? What if you have a frequency that you want to pass all other frequencies, but you have a particular frequency that you don't want to get through? I mean, maybe we want some parental control on the radio. We don't want a certain radio program to get through, right? We could put that kind of a filter on it, couldn't we?
You apply that as like a radio jammer?
Oh, probably. Yeah, I mean, jamming radios is not that tough. We used to do it. There used to be above the electrical lab, there were secretaries, and we would just take the function gen. Probably shouldn't tell you this, but I think we're probably okay. But yeah, we're being tape recorded. But what we do is we just take the function generator and put a wire out of the function generator. So basically, put an antenna on the function generator and just run it through its frequency until you hear the radio fuzz up. Okay, and now you're broadcasting on their frequency, and then they'll find another frequency because obviously that one's not working for them. So then you'll have to change. So, yeah, I got to figure out how to edit things. So. I don't think I broke any laws there because I was low wattage, so I was just an annoyance, not illegal. Yeah.
We have this thing where, like, in our motor room, if you flip on a fluorescent light, the radio will just cut out. So is the light like?
Yeah, I mean, that fluorescent light probably has a ballast that has all kinds of magnetic energy around it. Yeah, it's probably not going to like that. If you want to listen to electrical noise and whatnot, flip your radio to AM and drive around town. Every time you get close to a power line or transformer or whatnot, you'll hear it fuzz out. So, I think my car, all it has is an AM radio. I'm still waiting for someone to steal it. I'm just going to laugh. Yeah, anyway. You get a lot of Hispanic channels. I've been working on my Spanish listening to that. I can get some. I like to listen to ones where they say it and then they'll interpret it, and I can work on my Spanish there. Anyway, so we got a notch. We'll actually be using this in lab next week, so you'll get a chance to use a notch filter. If we continue to talk about this, maybe we will have a filter that looks like this, which would be a low pass, right? So if we want to stick with radios and audio and things like that, what do we use a low-pass filter for? I don't think a lot of people build stereos too much anymore, but people that do that kind of business, you take the audio signal and you'll separate it, right? And you want your low frequency to go to what speakers? Yeah, your subwoofers, the big speakers, right? Okay. Or we could have something like this. We could have a high pass, because if our frequency is here, as the frequency gets higher, it starts to pass it, so this would be a high pass. Where would we want that signal to go in our audio system? Little tweeters, right? Okay.
Now, we use this for a lot more important things than probably audio systems, although there's points in people's lives when they think there's nothing more important than an audio system. But let's say that we have a signal here. We're expecting a square wave, but we don't get a square wave. We get a whole bunch of noise on this thing. What could we run that through? Well, if I ran it through a low-pass filter, would it continue to pass the low-frequency signal? Yeah. And would it stop? Would it attenuate this high-frequency noise? It would, wouldn't it? So a lot of times if I want to get rid of that noise, I'll run it through a low-pass filter. What could, if it's a low pass, it keeps the low frequency, which is the bass wave, and it gets rid of this high frequency that's the noise.
Oh, that's only the high frequency is the noise on that square.
Right. You have two waves here. You have the square wave that is a low frequency event, and then you have the noise that is a very high frequency event. Okay. So you're going to try and get rid of that high frequency. Where could we use a high pass filter? I think I used this example maybe last year when we talked a little bit about this in GE. We talked about it in passing just to give you something to calculate. But if I was talking about things of national security, would this be a consequence to national security? Would this be a good room to do it? Probably not with the windows open, right? If we close the windows and close the blinds, would this be a better room? Not really. Could you figure out what I was saying by observing those windows? Yeah. Yeah, I mean, as I'm talking, I'm causing the windows to vibrate. As you're talking, causing the windows to vibrate. I don't think so.
The computer is like trying to kill everyone, and they go in this room to try and hide from the computer so it can't hear them.
My computer tries to kill me on a regular basis.
Then they notice a cup on the table. And it figured out what they said from the vibrations of the water.
Yeah.
And
Well, probably what I'd be more worried about is someone sitting in the bushes over there with a laser bouncing it off the windows. But they're going to have a problem as we talk. Our voices are rather high frequency, right? But there's other events that are happening in here. People scooting their chairs, doors opening and closing, the heating and cooling system coming on and off. Is that going to vibrate the windows? You bet. What are those events, though? Those are low frequency. So if I ran my measurements on the window vibrating through a high-pass filter, I would stop all of that low-frequency noise that I don't want, the doors opening, the heating and cooling coming on and off, and I'd just get the high-frequency voices, wouldn't I? Yes?
why is it that a voice is a high frequency and other voices is low?
Well, I'm talking not so necessarily talking about noise, but rather events. Okay? I mean, whether the door makes a noise or not when it closes, it causes a pressure in here that will cause the windows to vibrate. It's just it doesn't happen as fast or as much. So there's some different types of filters that we will encounter. You probably have heard the term bandwidth. Eventually we'll talk about this point here, where we'll talk about an omega 1 or an omega low, and an omega 2 or an omega high. And the difference between those is going to be the bandwidth. So we'll talk about all of those when we get together next time and talk more about these filters and how to analyze them. So take care till then. Thank you.